So what we're going to do now is we're still dealing with limits. We're not done with limits, but we're going to look at what happens when functions approach both vertical and horizontal asymptotes. We're going to start with vertical asymptotes. So hopefully you're all familiar with how vertical asymptotes occur in graphs, right? It's when we have the denominator equals 0 at a certain x value, but the numerator gives you a regular old constant there. So like in this case, f of x equals 1 over x minus 2. If x is 2, we end up with 1 over 0, right? And that tells us there's a vertical asymptote at x equals 2. Should have done that lots of times dealing with rational functions over the last couple of years. I hope.
Yes.
Yes. All right, cool. So anytime a function approaches a vertical asymptote, we then say that the limit as we approach that x value where the asymptote is, either from the left or from the right, is either infinity or negative infinity, because it is not approaching a specific real number value. It's getting very, very, very large or getting very, 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 very small. We say that it's either increasing without bound or decreasing without bound. So if I look at the limit as x approaches 2, which is my vertical asymptote here, from the right-hand side, my function is going up as it approaches 2 from the right, and we would say that that limit is infinity. And if we were talking about a limit as x approaches 2 from the left, we'd be looking from the left-hand side, and it would be going down towards negative infinity. So infinity or negative infinity would be an acceptable response for either of those limits. But what we need to keep in mind when we're doing all of these infinite limits is that anytime the answer to a limit comes out to be infinity or negative infinity, technically that limit doesn't exist, because our official definition of a limit says that it has to approach a real number, an infinity or negative infinity. They're both not real numbers. Everybody good with that?
Yeah.
So we say infinity or we say negative infinity just so we have a general idea of what the graph is doing, how it's functioning, but technically those limits don't exist. And if this was the AP test and it was like a multiple choice question, the answer, if it asked you what's the limit as x approaches 2 from the right of f of x, with f of x equal to 1 over x minus 2, they might put infinity as an answer choice, or they might put does not exist as an answer choice. They wouldn't put both of them, but they would put one or the other of those, and you should know that it could be either one. Everybody cool with that? Makes sense to everybody?
Yes.
All right, spectacular. Okay. And clearly, if we were asking about the limit as x approaches 2 of this function, we would obviously, since there's an asymptote there, be able to say it doesn't exist no matter what. But if both of these happen to have been infinity, we could have said it was infinity. Or if both of them happen to be negative infinity, we could have said it was negative infinity. But we can say that it doesn't exist, which tells us that these certainly are not even approaching the same infinity. The one's approaching positive and the other's approaching negative infinity. So 3 different options on it. One is at the asymptote, it's approaching infinity from both sides. Could be approaching negative infinity from both sides. Or like the one we were just looking at, could be approaching negative infinity from one side and infinity from the other. All of these are perfectly acceptable. We want to be able to go in and just by looking at the equation of the function, figure out what the vertical asymptotes are and figure out what the behavior is as we approach from both sides, whether they're both approaching infinity, both approaching negative infinity, or one on the other side and the other on the other side. So all 3 of these are options. Let's take a look at this one, f of x equals 1 over x minus 4 to the 3rd power. And without graphing it, we're going to figure out the one-sided limits and the two-sided limit at the vertical asymptote. So first off, what's the vertical asymptote of f of x?
4.
Yeah. All right, so our vertical asymptote ought to be x equals 4. It's that vertical line x equals 4. So what are we going to do? The limit from the left or the limit from the right first? I'll leave it up to you all.
Limit to the left, I guess.
All right. The limit as x approaches 4 from the left of 1 over x minus 4 cubed. Let's think about what happens when we plug in a number very close to 4 but from the left side. What's a number that's very close to 4 on the left-hand side of 4?
3.
3. Okay, that's pretty close. Anybody got a closer number? Not to like discourage you from shouting things out. 3 is good, but can we get closer? What's closer than 3?
3.9.
3.9. That's even closer. Wow. Can we get even closer than that?
3.999999999999999999999.
Perfect. That was the exact answer I was looking for. Okay, 3.99999999999, as I often say, like I just go on and ramble these nines forever, right? Well, if I plug in that number, 3.99999999999, and I subtract 4 from it, what do I get? I get 1 over a very, very small number, right? I'm just going to use a real technical term here. I'm going to get a very small number. And is that very, very small number positive or negative inside those parentheses?
Negative.
Right. It's a very small negative number, and I'm going to cube it. What happens if I take a very, very small number like 0.0000000000001, sorry, negative that, and cube it?
It becomes way smaller.
Yes, it becomes much, much smaller. It becomes even smaller. And is it still negative or does it become positive?
Negative.
Still negative. But there's an even smaller negative. And what happens if we take 1 and we divide it by an exceptionally small number?
The number is exceptionally big.
It becomes very, very large, actually. And in this case, it becomes a very, very large negative. So we will say that this is negative infinity, which tells us that as we approach 4 from the left-hand side, this function is dropping down as it hits that vertical asymptote. It's going towards negative infinity. Everybody good with that?
Yeah.
All right. What about the limit as x approaches 4 from the right of f of x? Well, as I approach 4 from the right, that's going to be a 4.00000000001 minus the 4 gives us that 0.000, etc. 1. It gives us 1 over a very small positive number that is being cubed. And if we cube a very small positive, it becomes an even smaller positive, which gives us, in this case, positive infinity. Everybody good with that?
Yes.
And the limit as x approaches 4 of f of x, we'll say does not exist. Technically, none of these 3 limits exist, but one of them we knew was negative infinity, the other we knew was going towards infinity. And since we're not approaching the same sign of infinity, we'll definitely say this one doesn't exist. Good or no?
Good.
Cool. Let's do another one. We'll do this one a little bit more quickly. First off, what's the vertical asymptote?
Positive. 2.
Of the x equals 2. So we are looking for a limit as x approaches 2 from the left of f of x. That'd be like plugging in 1.99999999, which is going to give us a very small negative down there that we are then squaring. And so what do we end up with?
Positive infinite. Oh.
Yeah, but we get 1 over a very positive, which gives us positive. So that's squared. And what if we look at limit as x approaches 2 to the right of that? Well, that's just 1 over a very small positive squared, which is still 1 over a small positive, which is then positive infinity. Good or no?
Yes.
And so we could, if we wanted to, say that the limit as x approaches 2 of f of x is also infinity, even though we know that technically none of these 3 limits exist. Good, bad, indifferent?
Good.
All right. Last one of these that we will do. First thing we have to do is figure out where the vertical asymptotes are. So how do I do that? I need to factor that denominator. What does that factor to? X, what?
X minus 3 times x minus 1.
Wonderful. Which gives us vertical asymptotes of x equals 3 and x equals 1. So here we're now going to have to be a little bit more careful, since we got two different things going on down there. It's not just a squared or a cube, it's actually two different little binomials. You guys want to start with doing x equals 3 or x equals 1?
1.
All right. So if we're going to look at the limit as x approaches 1 from the left of f of x, what's the numerator going to be? As we get very, very close to 1 from the left-hand side, this is essentially going to be a 4 in the numerator, isn't it? Just plug in the 4. And then what about this x minus 3? That's just going to be -2. And then as we approach 1 from the left, that's like 0.9999999 minus 1 is a very small negative number, right? So what should this come out to be? The negatives cancel out, right? Makes it a positive.
Positive infinity.
Large positive number.
Right, should be a large positive number, right? The very small number down here, even if I multiply it by 2, still a very small positive number, and 4 divided by a very small positive is infinity. Everybody good with that?
Yeah.
All right, what about as we approach 1 from the right? We still have a 4, and we still have a -2, but now we have a very small positive number down there, which is going to end up giving us negative infinity. Good or no?
Good.
And what does that tell us about the limit as x approaches 1 of f of x?
Not exist. Does not exist.
Good. All right, and real quickly, we'll do this for 3, just to make sure we got the idea. As we approach 3 from the left, what's the numerator? I know that arithmetic is hard, but 3 times 4 is 12, right? And if I'm approaching 3 from the left, this x minus 3 is a very small negative. And 3 minus 1 is just 2. So what does that give us? Negative infinity. And as we approach 3 from the right, we've still got 12, and now we've got a small positive times our 2, which is positive infinity. And the limit as x approaches 3 of the function doesn't exist. And remember, technically, all 6 of these limits that we just found don't exist. Good or no?
Yeah.
Anybody having any issues with these ideas of these vertical asymptotes? Okay, great. So now, instead of looking at vertical asymptotes, we're going to look at what happens as our x values get very, very large, not as our y values get very large or very small at vertical asymptotes, but what happens as x goes towards infinity. So what would you get if you put in a very, very large number for x here?
Really close to 2.
Yeah, we get 2 plus 1 over infinity, 1 over a huge positive number. And 1 divided by that huge positive number is effectively 0. So if we add 0, we get 2. What is this graph going to do then as x goes towards infinity?
It's going to go really approach down to 2.
Exactly. And
Oh,
what do we call that? What happens?
Horizontal asymptote.
Would be a horizontal asymptote. Exactly. Trying to get up. There we go. I got this. 2 plus 1 over x, right? And if we look, yep, sure looks like as we go out here towards x getting large, it looks like it's approaching that horizontal asymptote of y equals 2. Everybody good with that or no? Didn't mean to do that. That's what I meant to do. All right. Everybody good with that? We're getting a horizontal asymptote. So anytime we look at a limit as x approaches infinity, it should be giving us a horizontal asymptote. Good?
Good.
All right. Perfect. So let's see if we can use some rules for limits to find the horizontal asymptote of 2x squared minus 5 over 3x squared plus x plus 2. Now you should already have a general idea of what the horizontal asymptote of that is because it's a rational function and you probably learned some rules for horizontal asymptotes for rational functions in the past. Does that sound familiar?
It's something like you need to divide the coefficients of the leading thing or something like that.
Right. It sort of depends on what the degree of the numerator and the degree of the denominator are. But the rule, one of the rules is, if the degree of the numerator and the degree of the denominator are the same, you divide the leading coefficients, right? And that's what your math teacher told you. And you were like, cool, this one's y equals 2/3. I don't have to do any work. But the reason that you're able to do that is calculus. We look for the limit as x approaches infinity of this particular function. And one of the ways that we can evaluate this limit, we're going to learn some other ways in the future, but for today, the way that we're going to learn to evaluate this is find the highest degree, whether it's in the numerator or the denominator, or if it's the same in both, find the highest degree and divide everything, I mean, literally every little piece of this rational function by that highest degree. So I'm dividing everything by x squared because x squared was the highest degree. And so I'm going to write this out as the limit as x approaches infinity of 2x squared over x squared. What's 2x squared over x squared? It's just 2, right? Minus 5 over x squared. All over 3 plus 1 over x plus 2 over x squared. Everybody good with that? That's me dividing every little piece by x squared. And that's perfectly allowed, right? As long as I do it to the top, I have to do it to the bottom, but I can do that to everything, right?
Yes.
Okay. So this is why that rule works when the degrees are the same, because, well, what's left? A 2 and a 3, right? And a 5 over x squared. But as x goes towards infinity, what can you tell me about minus 5 over x squared?
Horizontal.
Well, what's happening to this number that is negative 5 over x squared as x gets very, very large? Like if I plug in 100 billion in here as x and then squared and do 5 divided by that, what is that number very, very, very close to?
0.
Very, very close to 0, exactly. And what about 1 over x?
Also close to 0.
And 2 over x squared is also, right? They're all very close to 0. And so effectively, all that is significant, all that matters is the leading coefficients of the highest degrees. So we end up getting 2/3. And so our horizontal asymptote is y equals 2/3. Everybody good with that or no? And that's where that rule that you can, if the degrees are the same, you can divide the leading coefficients. That's where it comes from. This
So
2 and this
cancel out.
3 dominate the numerator and the denominator, and the rest of it becomes 0. Sorry, what were you going to say?
So whenever the denominator is x or x squared or x to an exponent, you just cancel it out, basically.
Is the denominator of each of those pieces. If it's x going towards infinity, yes. Right?
Okay.
Because it's going to be some constant, even if this constant is really big, like even if this is a million up here, right? A million over x squared. Well, as x goes towards infinity, and I'm far, far higher up than a million, you know, I'm at a 1 followed by 10 billion zeros, and then I square it and I'm even bigger. I mean, that's still very close to 0. It still becomes insignificant.
Okay.
Good?
Yeah.
Cool. All right. Let's do another one. Let's use our rules for limits to find the horizontal asymptotes of this one. So it's a very similar one, except this time the degree of the numerator and the degree of the denominator are not the same. True?
True.
What's the highest degree that we have?
4.
4. So we're going to divide every term in this limit that we write. Ready? We're going to divide them all by x to the 4th. And what is that going to give us? In the numerator, 2x squared over x to the 4th is just 2 over x squared. And then minus 5 over x to the 4th. And in the denominator, we're going to have 3 plus 1 over x cubed plus 2 over x to the 4th. And what can you tell me about 2 over x squared as x goes to infinity?
0.
And what about 5 over x to the 4th?
0.
And 3?
The horizontal asymptote is 1 over 3.
No, it's not. What is 3 as x goes towards infinity?
3.
Okay, and 1 over x cubed is 0, and 2 over x to the 4th is 0. So we end
Oh,
up
wait, 0 over 3. Oh, it's like, okay.
0 over 3, which gives us 0, telling us that our horizontal asymptote is y equals 0. And that was the rule you should have learned a year or two ago, that anytime you have a rational function and the degree of the numerator is smaller than the degree of the denominator, you get a horizontal asymptote of y equals 0. That was one of your rules. You guys remember that rule?
I do now.
All right. Hey, you'll never forget it now, because now you got to do all this extra work to find it. All right, one more case. We had the case where the degrees were the same, the case where the degree of the numerator was less. Now we have the case of where the numerator is more. So our highest degree is x cubed, which means we're going to divide everything by x cubed. So we're going to look at a limit as x approaches infinity of 2x cubed minus 5 over x cubed, all over 3x squared plus x plus 2 over x cubed. And the 2x cubed over x cubed is 2 minus 5 over x cubed. And then we got 3 over x plus 1 over x squared plus 2 over x cubed. And as x gets exceptionally large, what is 2?
2.
2. And 5 over x cubed is 0. And all of these terms are also 0. We get 2 over 0, which is undefined. And if it's undefined, that means that this limit does not exist, and there are no horizontal asymptotes. And that should have been the rule that you learned about the degree of the numerator being more than the degree of the denominator. Good or no?
Yes.
All right. Now, I would love to continue and just keep lecturing for the next hour or two, but we're not going to have enough time to successfully get through the next problem without me being annoyed that I had to rush through it and nobody understood what I was doing. So we've done the basics of limits at vertical and horizontal asymptotes. There's quite a bit more to the horizontal asymptote ones that we will deal with because we've only dealt with these rational functions. We're going to have to deal with things that are not rational functions. But I guess we're going to save that for Monday.